When we introduced matrix multiplication, we noticed that matrix multiplication has an identity matrix. In fact, it has one for every size. But we never asked the corresponding question about an inverse for matrix multiplication. Anytime you have an identity for an operation, you should ask the corresponding question about inverses. We did for addition, right? For matrix addition, the identity is the zero matrix, and right, that's the identity for the addition operation, because if you take any matrix plus the zero matrix, you get the same matrix. And this lets you ask the question about inverses, because you can ask, well, now that I have an identity, is it possible to come up with a matrix so that when I add it to A, I get the identity? And this matrix would be called the inverse for the operation. So this is an additive inverse. For addition, there is an inverse, it's just the negative. But we never asked the corresponding question for multiplication. So we have identities. Are there inverses? So what we're asking here is, if we have some non-zero matrix A, is it possible that there's a matrix that we will call A inverse, so that A inverse times A is the identity matrix of some size n, and the multiplication the other way around, A times A inverse, is also the same identity matrix. Now, it might seem a little artificial at the moment to require that both orders of the multiplication be the same size identity matrix, but it turns out that that has to be the case. So we don't quite have the tools to prove that yet, but if there is such a matrix A inverse, then it turns out that these two identity matrices have to be the same size. Okay, so with that in mind, let's suppose that A is m by n. Well, if A is m by n, right, this identity matrix is n by n. So this n here, that came from the number of rows in the first matrix in the product. So A inverse has to be n by something, but for this matrix product to even be defined, the number of columns of A inverse has to be equal to the number of rows of A. So that means this must be m here. Well, now let's look at this other product. So let me write it down a little bigger like this. So the identity matrix, the n by n identity matrix is n by n. A is m by n, and A inverse is n by m. Well, now this shows us, right, these n's match already, so the product is defined, but comparing what the sizes on the left to the sizes on the right, we see that, well, look, m actually has to be the same as n. So for a matrix to have an inverse, it has to be square. For non-square matrices, you can't have an inverse. So really, we should be asking for a square non-zero matrix. Of course, we have to have a non-zero matrix because any matrix times the zero matrix is zero. So for the zero matrix, there's no hope of having an inverse. So really, the only question is, for non-zero square matrices, are there inverses? Well, let's look at an example. How about this matrix? If there were an inverse, it would, so right, here's our matrix. If there were an inverse, A inverse, we don't know what it should be, so let's just use variables for all of its entries. Since A is 2 by 2, A inverse also has to be 2 by 2. But if there were such a matrix and we did this product, we would have to get the identity, because the 2 by 2 identity, because that's what it means to be the inverse, right? This being an inverse means that when you multiply it by A, you get the identity. Well, we can work out the stuff on the left. If we actually do this matrix multiplication on the left, we get, let's see, A and then 2A. And over here we get B and 2B. Okay. And that is supposed to be equal to 1, 0, 0, 1. But this is a problem because if you look at the upper left corner, this says that A has to be 1. But if you look at the lower left corner, this says that A has to be 0. So what we found here is if there is an inverse, then little a has to be 1 and 0. But that can't happen. So for this particular matrix, there is no inverse, even though this matrix is not the 0 matrix. So this is one troublesome thing about matrix inverse. With multiplications, we're used to anything that isn't 0 having an inverse. But for matrices, that just isn't the case. It's possible to have square matrices that aren't 0, but still don't have an inverse. So that's one thing to keep in mind. Another basic question we should ask about the inverse is it possible to have more than one? It's not really obvious if it is possible to have more than one matrix inverse, or if it's only possible to have one, right? For real numbers, we know that if you have some real number, or some scalar r, there is a unique number that is the reciprocal of r. But for matrices, we don't really know if that's the case. And our intuition for what makes sense is failing us with matrix multiplication, because matrix multiplication isn't commutative. Non-zero matrices might not have an inverse. So we have to be really careful and not make assumptions about how this matrix inverse idea works. So let's see, is it possible to have more than one inverse? Well, suppose there are two. So suppose that B and C are inverses for A. What does that mean? Well, that means that A times B is the identity of some appropriate size, whatever size that is. Also, it means that B times A is also the identity of that size, and C times A and A times C also have to be the identity for that size. Okay, so is it possible to have more than one matrix inverse? Well, what we're really asking is it the fact, or is it a fact, that B is equal to C? So if we could fill in some sort of calculation here, then we would know that they're equal. And, well, it's not really clear what's possible to do here, but we don't have many options. I mean, the only thing that we could possibly do is, right, we could add 0 or multiply by 1. Those are the only two options. But when I say multiply by 1, what I really mean is multiply by the identity, right? So these two things are definitely equal because B is equal to B times the identity matrix. That's what makes it the identity matrix. But if you look up here, we have a lot of choices for what we could plug in here for the identity matrix. In particular, we could choose, say, A times C. So then we'd have B times the identity matrix, which is A times C. But we noticed that matrix multiplication is associative, so we could move those parentheses over to here, B times A times C. But B times A, that's the identity matrix again, times C. And of course, the identity matrix times C is C. So here we have a big calculation that shows us that B is actually equal to C. So if there is a matrix inverse, there is only one of them. So the matrix for any given matrix A, its inverse, should it exist, is unique.